All right, folks. Well, hey, welcome. Thank you for having me again. I'm excited for the next, I'll say 25 minutes. We want to leave some time for questions. If you have questions during the webinar, I think, Dave, you can help with those. So just, guys, type them in on the right-hand side of the screen. But let's get into it. And a little bit about myself. I've actually been using SolidWorks, probably about 14 years now, starting back in college. And I started with SimXpress. It was the first FEA tool that I ever touched. So, like Dave mentioned, it's actually in every single seat of SolidWorks. Most of you are probably using it today. So I want to talk a little bit about what SimXpress can do, but then some of the limitations I'm sure we've all ran into as we use it. And then I'll talk about really what the rest of the portfolio looks like and what the capabilities look like to make sure that we're getting the best results to get the best insight into our design. So I'm going to spend a couple minutes. Anyone here new to simulation, I'm going to talk about, well, what it is. Then we're going to go through a project today. And the project should be pretty interesting. We're going to look at an analysis of a steering suspension assembly. And we're going to do it two ways. We're going to do it in Express, and then we're going to look at some of the expanded simulation results and see, are they different? Are they giving us the same answer? And what else can we analyze about the project? We'll then look towards design iterations. How can we make this design better? And then finally, new ways we can test it. What about fatigue or frequency or harmonic response? So there's so much we can do with the rest of the simulation portfolio that helps us get some more results, get this project done quickly. So what is simulation? Well, we kind of use that term broadly at SolidWorks and DASI. I mean, simulation to me is really FEA or CFD, but there's a few more capabilities that we have inside of the simulation portfolio. It really all depends on what you want to test. So simulation is kind of that broad quadrant in the top of the SolidWorks products that you guys all probably use today. And, you know, like I said, it's simulation, it's flow, but it's also the rigid body kinematics in motion. It's also the plastics analysis to see if your part is moldable, as well as sustainability analysis to take a look at the ecological impact of your part. So I kind of break simulation, just so we're all on the same page here, into these five realms, if you will. The structural analysis, the fluid or heat transfer, the rigid body kinematics, the plastics, and sustainability. And of course, today we're really going to focus on the top left area, which to me is really the bread and butter of simulation activity, right? Linear statics, the stuff that we're trying to do with SimXpress day in and day out. So just so we're on the same page, FEA, structural analysis, CFD, rigid body, injection mold, and then ecological, or you could call it a light life cycle analysis screening. So that's what we mean by simulation. All right. So a lot of you have probably been using simulation. Like myself, I've used it for a while, pretty much all inside of SolidWorks. So I've had a lot of years to kind of get good at this stuff. And I've also got good at explaining to either laymen or other managers in my company who don't really get what simulation is. I explain it to them like this. We all have a GPS to navigate us around traffic. So I live actually out in the Bay Area in San Jose. So whenever I'm going around, I always bring up my Google Maps or my Waze app. And I know the route, but I don't know the optimal way to get there given the traffic of the day to get there in the fastest time. So I look at simulation as a GPS, and that's kind of versus our old tried and true, beam hand calculations, or I like to look at it as the map and pencil and compass, where sure we can draw out the best route, but does it get us to the final destination faster? Does it get us from that initial to the best design in the most optimal path without wasting a lot of cycles and a lot of time, building prototypes or using, express tools when we could be getting to our job, getting to our final design faster and smoother using a more automated tool. So we're going to talk more about things like optimization later, which can really automate and get us the best design faster. Because really at the end of the day as engineers, what are we trying to do? We're trying to start with an initial concept, a sketch, a product that we already have on the shelf, and we're trying to make it better. And a lot of times we use simulation already today to make sure it's safe. And most of us using SimXpress today understand that the result we're looking at is typically deformation or, more importantly, a factor of safety. Is this thing going to fail? But there's so many more characteristics we can evaluate using simulation. Things like durability or life. Is it vibration resistant? Is it cool enough? Is it sustainable? So we're going to see an example of that as we apply it. So let's get into the good stuff now. Enough of the intro. Let's talk about our study. And I mentioned the project for today as the steering bracket, and more specifically, this is actually a steering bracket assembly from a Group N rally car. And what we want to do is kind of set up a test to represent the worst case loading. And this might be what we put in the test fixture to make sure that our design is okay. And of course you can imagine that lightweight is going to be a goal in this design to make sure that we can win our races and minimize the mass on our vehicles. So that's the geometry that I have today, and we're going to start off with really two goals. Let's look at the geometry and design for strength. Now specifically, since I'm really interested in keeping this thing lightweight, we're going to maybe cut it a little close, but I'm going to go for a factor of safety of 1.5. All right? So keep the stress below 30,000. I'm going to start off by using 6061 aluminum, so hence the 30,000. And then also, if I see an opportunity to reduce the weight, let's go ahead and take it. So I'm going to need some insight from the results. So I'm not going to actually run Express because I want to spend my time showing you the rest of the tool set, but I did save this out as a part and go into Express. And all of you who run Express know that one of the fundamental things you have to do with your assembly is save it out as a single part and then combine all the bodies, because SimXpress really expects a single body. And that's okay for some designs. So in this case, that's what I did. I took kind of a subset of the assembly and I just saved it out, and what you see is basically the results from SimXpress. So a max displacement of about, 23 thousandths of an inch. Not too bad, but really more importantly, we're looking at the stress as my main design criteria. We see the max stress is, about 26,000 psi, giving us a factor of safety of 1.54. So, given this worst case, this testing load that we're going to go put in the field, this thing passes, right? And job's done, let's move on to the next thing. Right, but not so soon, right? There's a lot of assumptions that we made when we used Simulation Express to run this analysis. So even though the pretty pictures tell me it's okay, well, there's some things we got to make sure that we disclose if we're going to use this as design feedback or validation. So some of the assumptions that we make, the biggest one to me that I always run into as soon as I want to do a more complicated system or an assembly is that SimXpress expects a single homogeneous body, right? One single part. And that's kind of hard to do sometimes, is isolate one part out of our assembly. Like my bracket here, I can't just take out the bracket because what about the interaction with the other components? So what we end up doing is combining them all together, right, into one body, saving as one part. And that's what I used to do in school all the time because I only had the SimXpress. So single homogeneous body is a big one. And of course, that also means that we can only have one material. So in this case, if I want to try different aluminums, maybe some 6061 and some 7075, I can't do that because it expects one body, one material. Limited system interaction, to me, like I said, is if I have an assembly, there might be some more complex interactions, such as contact pressures, bolted fasteners, frictional contacts, that I can't take into account because we're kind of fusing it all together into this one massive body. A couple other limitations that aren't really key in this analysis, but I do run into from time to time, would be the limits on the restraints. You know, you can fix things in simulation, which is probably your bread and butter restraint, but also there's some other cooler restraints that you can do in the full simulation that, again, allow you to get better results, more accurate results, faster. Because, again, a fixture represents everything that you're not modeling. And sometimes a 100% rigid fixture isn't necessarily the best. Also, we're limited to forces and pressures in SimXpress. In this case, that works fine, right? We just have an 1,800-pound force kind of normal to the direction of the bracket, and that's okay. But there's also some other functionality we'll take a look at that might enable, again, more accurate and better results. Another thing is the mesh sensitivity. You know, in Simulation Express, you can set the mesh density, but you can't do what we call local mesh controls, which are really key to make sure we get accurate results. We like to refine the mesh where we have the high stress concentration to make sure we're getting the most data points there. And finally, as we'll see as I go through the full software, there's a lot more result types that you can pull out to get insight into your design that a basic stress or factor of safety or displacement plot doesn't necessarily give me. So let's move on. I want to save enough time and show you the software and how I'm going to set this up given the full package of simulation that I'm just, I guess, lucky enough to have because I get to work for SolidWorks. But when I first got this in industry and I got the real simulation, I'm like, oh my gosh, I had no idea that SolidWorks could actually do all this because I thought Express was the limitation of what we could do for FEA, and really it's just the tip of the iceberg. So let me go into SolidWorks and show you a little bit about what we can actually do with a full simulation. So here, of course, I have my assembly. Let me rearrange the windows. And just a basic four parts. I suppressed all the fasteners in this one, and we'll see why in a little bit. So let's actually run through and spend a couple minutes setting up a simulation not in the Express. If you're using Express, you're familiar with the step-by-step wizard, which again is great if you're a student, a new user, or not familiar with FEA, or you use it a couple times a year and you don't, if you have a lot more important things to remember than the setup steps. But really just creating a full simulation study is just as easy, and I'll show you that right now. So when I start simulation, when I have the real package, of course, I have a lot more options in terms of modules or tests that I can run. And we'll do a couple of them here in about 10 minutes. But obviously static, right? Linear static are bread and butter. What's my factor of safety? Is it going to fail? What does my deformation look like? So we'll begin a new study. And on the left-hand side, you'll see the tree, which may look familiar to you guys. There's also a wizard. If we want to go through and do a study advisor or an advisor for my fixtures, I can bring up that old wizard that we use in Express. But after you do this a few times, you can kind of eschew the wizard and just go right towards the tree. And really think of it going in the tree top to bottom and setting things up. And then when we're done, we'll see results on the bottom. So first of all, notice that the parts are 4 different bodies. So each part in my assembly, or I should say each solid body or surface body, in fact, can be a separate entity. So they can actually have separate materials. In this case, like I mentioned, we're going to start off and just apply a 6061 T6 material, right? Some pretty common, kind of middle-of-the-road aluminum. But, as we'll see later, there might be a couple pieces that I might want to choose more high strength. So the first benefit here of the real simulation is I can mix materials, which probably better represents real-life designs. Now, connections, this is that system interaction. This is how everything works together in the assembly. All right? And remember, in Express, everything's fused together. And by default, you can run that in simulation just like that, with the same assumptions. We call it global bonded. Basically, everything that's touching in your assembly, just glue it together. And in fact, for a lot of designs, sometimes it's good just to start there, make sure it's all set up right, and then add more complexity. But since I already know this is going to work okay, I'm going to edit this, and instead of doing global bonded, instead of fusing everything together, what I want to do is more represent the real-life condition where things aren't welded or fused, they actually have friction and contact between them. And that's what we call a no-penetration condition. Basically, the parts can interact, they can contact each other, and they'll just push off each other with normal force. I can also include a friction factor to more accurately represent the aluminum on aluminum contact. And here's just a factor from 0 to 1. I'll put in just 0.15. It doesn't matter too much in this analysis because things aren't really sliding back and forth, but that might be more important depending on your design. So no penetration is, like I said, a little more accurate than bonded because it's going to allow the parts to actually come apart but not pass through each other, hence the no penetration. And we'll kind of see that in the results. Now, the fixtures, that's actually the same. Notice I have a lot of different fixture types here. I'm still going to use fixed just like I would in Express, but notice there's a couple other advanced ones that we might use, again, depending on our system. Things we might be familiar with from statics, like our roller sliding, or a fixed hinge restraint, or other things like actually giving it an elasticity so it's not 100% rigid. Anyway, well, let's apply a fixed geometry, and I'm just going to simulate kind of the physical test here where we just bolt the wheel lug holes here 100% rigid. So notice on the left-hand side you can see I can flip to the different restraint types if I want to, but actually we'll see in the results that the real stress concentrations, the real results of interest are going to be in the bracket. So I'm just going to kind of fix this rigidly, and we're not really going to look at this casting. It's just kind of a simplified version of it anyway. If I wanted to, I could get more advanced, and this is where the power comes into the full simulation. I can actually choose specific degrees of freedom that I want to restrain. So maybe these things are just on shafts, and they're allowed to move axially but not radially. So I could do that as well, creating these types of restraints. We're going to kind of bolt those down 100% rigid. But what about the rest of these things? Since these parts are no penetration, they need to contact each other. They still need to be connected. And the way I'm going to connect them is by using a virtual connector. So notice I mentioned I suppressed my fasteners, my bolts, my 3 bolts that I have here. In the real simulation, I have something called pin and bolt connectors. And these let me represent fasteners without actually having to have them in the simulation and solve them. And then what I'm able to pull out in the results is going to be either the factor of safety or the free body forces on those fasteners to compare to allowables. So in this case, I'm going to do a bolt connector. And actually, if I kept my toolbox fasteners in here, it would automatically convert, but I wanted to show you the setup here. So I'm going to choose just a regular, we call it a standard or counterbore screw, but basically I'm going to tell the software this is where the head of the screw would rest, okay? And then here is where the threaded area is going to be. All right, let's go ahead and pin that. I'm also going to give it the material. So we're going to get fancy here. Let's actually use, say, some 7075 T6 fasteners. And I'm going to tell the software there's a preload. And I was going to look this up. I'm not sure. Maybe some of the audience would have a better idea what the torque would be. But I can actually include that in the analysis. I'm going to do 100 here. You can actually include that in the analysis, which will give pre-tension to the system. And we'll actually see the stresses that develop in the fastener, as well as that'll increase the stiffness of the system with that preload in there. So just kind of go around, apply a couple more bolt connectors. Really easy to use. I'm just, again, clicking the edge, shift clicking into this part, hitting OK. So it's super easy to set those up. And then on the tree, you can see they're all here grouped together. So if I want to go back and maybe change the definition, you can do that. You get a little visual indication of the blue bolt. Again, don't get worried about the hex head. It's not really making, a hex head. It's actually doing a circular imprint. But it shows me that, hey, you've remembered to put bolt connectors there. I can also kind of verify that my connections are set up right by looking at a contact visualization plot. And this just shows me in the software how the solver is going to look at the interaction. And you can see it's kind of small, but in the top right it says no penetration. So it's actually showing me that it's validated that all these parts are not going to be fused or bonded. They're actually going to have frictional contacts next to each other. The last thing we'll do, actually two more things. We got to set up the load. Can't forget that. It wouldn't be a very exciting response if I didn't add the force here. So this is the same as Express. You just pick a force, you pick a direction. I'll do 1,800 pounds of force. Right, easy enough, and we're just going to choose that direction there. Final thing is the mesh. Now there's two very important things about using the mesh in full simulation that you can't really do in Express that I use all the time to make sure I'm getting the best results. The first thing is a local mesh control. So when I right click on here, there's a thing called a mesh control. This just means basically make a finer mesh in area of interest. Now since I ran this in Express, you guys don't remember, but I was looking at the plot earlier, and these were really kind of where the hot spots were on these faces. So what I'm going to do is tell the software, hey, make this mesh super fine on these faces where I'm going to see the high stress, thus making sure I get a better converged answer where the high stress is. The other thing I'm going to do is use a different type of mesher. So standard mesh is what you see in the Express, but in the real simulation I have access to what we call curvature-based. This is something I think in 2009 we released, and it's the default one that I use. And what you'll notice about it is it meshes and it automatically refines itself around curves. So you can see it has a very broad element, and then it narrows down as it goes through curves, so hence curvature-based. What it means is basically I can get a pretty robust optimal mesh without doing much manual control or iterating on the size, because it'll kind of adjust itself. So that's the setup. I always save before I run, in case I run out of memory. That's not really a problem on this one, but bigger and bigger assemblies, got to make sure you save that, because you can create some pretty gnarly large meshes. And we'll go ahead and run it. And honestly, this takes the trade-off here. SimXpress takes about 30 seconds to solve this. Since I'm running a contact friction problem, this one actually takes, I think, about 7 minutes to solve, because it's trying to figure out all the interactions between the parts. So I'm going to flip over to one that I already have finished over here. Okay, so same setup. Oh, I actually added gravity in this one, which, you know what, doesn't really matter, but it's another force type that you could apply in the full simulation for a bigger frame structure or something where gravity isn't negligible. And notice the results type that I have on my bottom left. Some of these are pretty similar. Some of them are kind of different. First of all, let's look at the displacement. I always look at displacement first. And the first thing you'll notice that differs from our Express is notice the bracket to the casting, the interaction here. Right? This is what that no penetration does. It allows that accurate representation of the response. So it actually peels away from the part, right? Because that's how it's going to deform. And of course, if you look in the upper left, 43 times magnification. So it doesn't actually peel that much. Yeah, so be careful about showing this one to the customer. It's just magnified so we can see the performance and the behavior of it. But you'll notice how it kind of contacts that and rubs against it, as well as notice how the pin, we're actually seeing the contact and bearing of the pin against the rest of the system. We're not just assuming that it's fused together. So overall, we're seeing 30 thousandths inch. This is pretty close. We had 23 thousandths before, so pretty close. And the difference is really because this thing is actually able now to peel away. So that's still fine. I mean, that's not much. But again, let's look at the stress. Now, before our stress was what, about 26,000 psi, and it passed? Now when I look at the stress, we're going to see something a little bit different. The stress is now a maximum of 42,000. So what gives? Well, for the most part, the stress around the geometry is the same. You know, where it's actually carrying the load is the same, but the interaction between the parts is now where I'm seeing the stress. Let's flip into an exploded view, and I'll show you what's going on here. So I'm going to leverage the assembly exploded view to look at the components, and here we kind of see it makes sense. Now that we have the pin actually bearing and contacting on the parts, we see the bending stress kind of bearing or impinging on the holes here, and you can see the stress in the pin. So the pin passes, but we can see we kind of have a problem here where we have the bearing stress on these through holes. Now another way we can look at that, let me collapse the exploded view, is what we call an ISO plot. And this is something I use all the time when I need to express to someone, hey, here's where we need to work on the design, or here's where it's over-designed. And an ISO plot, all it does, think of it like a high-pass filter. It's only showing me the stress that is above 30,000 or above my failure criteria. And we can move this up or down. And it's kind of neat. As we move down, we really get a picture for how the material is being used. So as I move it down, I start to get some more insight into the design. And maybe if lightweighting is a problem, or if lightweight is my goal, there's a lot of opportunity here to remove material in the middle. Anyway, we got bigger problems. We got some failure here. So the cool thing with simulation, of course, is you get some better results. You get the ability to do some cool plots. But of course, this gives me a lot more information about how my design is really going to behave than making the assumptions like it's all fusing together. We can also do the factor safety plot. So what I did here, I actually played around with a few different geometries. I actually tried thickening. And again, since we're in the same assembly, you can go back, we can edit component, we can change our thickness here. And so I played around yesterday with a bunch of different options, but at the end of the day, I just realized that, no matter how thick I make this, we still have that same force per area, and I couldn't get the stress below 30,000. So what's great about simulation is now, maybe I can explore something more fundamental, like taking the bracket and switching it over to a 7075 T6. Okay? So the 7075 material, that actually is what I ran yesterday, and when I look at factor of safety, even with the high stress, it actually passes now, 1.7, since I made the bracket out of 7075 aluminum. So I can play with mixing different materials together. So let me flip back to the PowerPoint real quick and just briefly talk about what we just did here. We looked at the contact, right, how we can set up more accurate interactions. We looked at how the displacement's pretty much the same, but how we got that real-life interaction between the components. But then we saw the high stress was actually because that pin was now allowed to bend and bear against the underlying bracket. So what I did is I tried a bunch of geometries. I used some results to figure out where the problem was, including an exploded view and an ISO view. And then I tried some design iterations. I don't have time to go through all these, but you guys can imagine. I tried thickening the bracket. I tried thickening this little leg here. I tried actually adding fillets, which actually reduced the area and made the stress higher. But you know what? I was just playing around in SolidWorks. And actually then I tried making the pin fatter. And each of these had some subtle effects. But at the end of the day, the real solution was to run 7075. Now, since I'm using 7075, a little more expensive, but also it's much stronger. The yield's, about 75,000 PSI. Now, all of a sudden, the bracket is almost over-designed. It's at 1.7 factor of safety. So something we can also set up is a design optimization, where I take some of the major dimensions or even fillet radii, and I set it up to automatically iterate through a design of experiments and figure out what's the lightest weight that still meets my minimum factor of safety. So I was able to set that up also inside a Simulation Professional, and you can see the setup right here. Oh, actually, I erased it because I was going to set it up, but we're running short on time. I'll skip that, but it's really cool. You set up all your parameters, set up your factor of safety constraint, and kind of let it chug. And the more parameters you have, the more you probably just want to set it up overnight. Okay, other ways we can test this assembly. Obviously, it's not just all about linear statics. I mean, that is our bread and butter, but there's a couple other failure modes we want to look at. So maybe my boss comes to me and says, hey, by the way, it looks good. You optimized it. You got the stress below the value. It passed the fatigue test. Or, sorry, it passed the physical test. But now you need to design for life. since we're doing such a low factor of safety, make sure that it can last 1 million cycles. So I need to do an accelerated life test. And then also, hey, do some frequency. Make sure that it's not in the range of 1 to 400 hertz, which is the road noise or tire misalignment kind of frequencies. We don't want this thing to start resonating or sending any kind of vibration up through the steering column. So of course that's something I can do right inside of SolidWorks with the modules. I can go to a frequency study, you set it up just the same, and then I can start looking at what my frequencies are. So my fundamental frequency here is 934 hertz, and I can go up and actually look through all the different frequencies, animate them, and really just make sure that I'm not going to be exciting them given the environment that I'm putting my component into. So here's a cool, interesting mode shape, 1800 hertz. Overall, this design is actually pretty good. It's pretty stiff, and we see that as I go up in mode, the frequency increases, and my first mode is actually about 900, so I'm fine in terms of the frequency study. I can also look at fatigue. Now, fatigue is a study that I can set up right inside of SolidWorks again, and I get two different plots. The most important one to me is the life plot. Hey, how many cycles am I going to be able to withstand if I apply that 1,800 pound load over and over and over again? So let me zoom in, and you can see here, right where we had that high stress, that's of course where we're probably going to see the fatigue failure, and the analysis tells me it's going to last about 2.4 million cycles. So it does exceed the 1 million cycle goal by about a factor of 2 to 1. So awesome. So I was able to use that simulation to just also verify that, hey, while I'm lightweighting, while I'm passing my factor of safety, I'm also not going to violate any kind of frequency or fatigue constraints. So this design checks out. So what we saw today is really, I think, why full simulation is important. You know, there's a lot of power in Express when you're getting going or you have single parts or small systems, but pretty soon you run into the limitations and the assumptions it makes in terms of system interaction, types of fixtures and loads that you can create, and the types of responses, the types of insight that you can pull out of your design. So I think we all understand, though, what simulation is all about. It's about predicting the performance, validating the behavior, and we want to make sure we do that accurately using the right tool. And of course, at the end of the day, hopefully allows you guys to get better products out there faster, get results to make sure it's not going to fail, and reduce that physical prototyping, hopefully reducing it to 1 cycle just to validate your simulation. I will mention, if you are using SimXpress today, or if you're brand new, you've never used Express, it's a great tool to get started with FEA, just like we did in school. So you just go into your SolidWorks, it's under the Tools menu or on the Evaluate tab, and there's actually a cool little link that says, hey, click for free training, and it brings you into this here where it'll take you through how to set up some Express, some exercises, some tutorials. So check that out. Like I said, it's a great tool to get started, to learn the setup, and then you can transfer that knowledge right away into using the full simulation. I talk to a lot of people who are kind of hesitant to use simulation because, maybe they didn't have time to study it in school or they never covered it. What's great is that when we survey our users, half of the people can master this tool in 5 days or less. And of course, Dave will tell you, most of the training classes, people leave that class, the simulation class, and they can go and apply it right away. It's a great training. But there's also a lot of online resources. There's also local simulation user groups. So don't be afraid that this is too much stuff. It's super easy to learn. Hey, even I could do it. What's interesting is when I really just want to learn something super fast, I don't have time to go through. I just need a quick tip. I search YouTube, or I search mysolidworks.com, and I search SolidWorks simulation. This was yesterday. I took the screenshot. Over 78,000 results. So if you want to learn more about simulation, kind of the capabilities, what it looks like, what's it like to use it, there's tons of videos up there, tons of resources to get a feel for it or to learn more about it. And at the end of the day, here's what the portfolio looks like. We started way back on the left end with static for the assemblies, but there's so much more that we can do. Right? We talked about the frequency analysis over here. We talked about the fatigue analysis, which is somewhere over here. The optimization to automatically lightweight. And then, of course, there's even more we could do with this steering bracket. What if we wanted to give it a random vibration or do some kind of impact test and not assume it was static? We can do all that inside of Simulation Premium. So tons of capability that we have, but that's all the time we have for today in our half hour. Dave, let me turn it back over to you.